So this is our second lesson on potential dividers. Let's look at our lesson objectives. So by the end of today's lesson, you should be able to explain how LDRs and thermistors are used in potential divider circuits and be able to answer questions related to how the potential difference across components within a potential divider circuit containing LDRs and thermistors varies as changes to the environment occur. So we need to start by just recapping what we know about LDRs and thermistors. You've already seen these a number of times. I mean, right back in year 9, we would have introduced them to you, but also in the first parts of this course, I know Dr. Cook's already talked about them in his IV characteristic lesson as well. So it's not the first time you've seen them. So let's start with an LDR. That's a light dependent resistor. The clue is in the name. The resistance of that depends on the light intensity shining on it. And what you need to remember is that as the light intensity goes up, the resistance is going to come down, and obviously vice versa. So if the light intensity goes down, the resistance is going to go up. The second is a thermistor. Again, there was a bit of a clue in the name, in the therm. This is a resistor that is affected by the temperature. Now, most components, most pieces of metal, as the temperature goes up, the resistance goes up. But with a thermistor, it's the opposite. It's really important that you remember that. So with a thermistor, as the temperature goes up, the resistance comes down. And again, obviously vice versa. So if the temperature goes down, the resistance goes up. So please keep that in mind whenever you're answering questions on potential dividers involving these components, because if you get that the wrong way around, you're going to lose marks. So really importantly, remember the kind of relationship between light intensity and resistance for an LDR and the relationship between temperature and resistance for a thermistor. So here we have a potential divider circuit. This circuit is identical to the ones that we had in yesterday's lesson. I've just rotated it through 90 degrees. I've done that because they sometimes like to do it in IGCSE papers, and I don't want the first time you see a circuit like this to be in an exam. If you tilt your head to the left, you'll see that this circuit is absolutely identical to the ones that were in the previous lesson. So there is no difference. Now, this component here is our thermistor. So that's the one that's going to be driving our changes in this circuit. Now, the kind of question you might get is something along this line, these lines. So what happens to the output as the temperature increases? Now, I just want to point out, I did this in yesterday's lesson and I didn't really kind of stress this enough, but I've been using abbreviations, a really simple way of laying this out. And that's fine for our notes, it's fine for discussing it in class. But if you're in an exam situation, I would strongly suggest that you write it out in proper Queen's English. Don't be using my abbreviations like I'm going to do now, but actually write in full sentences. So let's break it down. We're going to start with the temperature increasing, because that's what our question says, and let's think about what effect that is going to have on our thermistor. So from the previous slide, we should now know that as the temperature goes up, the resistance of that thermistor comes down. I then want to think about our all-important Ohm's law. So V is equal to IR. And if we think about this, if the resistance is going to come down, the voltage is going to come down. So we're going to have a decrease in the potential difference across our thermistor. So the PD across the thermistor decreases. We then need to consider the fact that these two are in parallel, and so the PD across them is always the same. So if the potential difference across the thermistor is decreasing, the potential difference across the output is decreasing. So we've got a system here whereby as the temperature increases, the output PD decreases. So you might have this in something like an oven. As the temperature starts to kind of get closer to the temperature that you want it to be, the potential difference across our heating element is going to decrease to slow down the rate at which it's heating up. We don't want it to overheat. So that's just one example of where you might use a circuit like this. Okay, another question that I want you to think about, and we're going to go through this on the next slide, is what change you can make if you want the output PD to increase as the temperature increases. So I want to completely reverse the function of this circuit. So at the moment in this question, we've got the temperature going up and the output PD going down. Well, how do I get the output PD to go up as the temperature goes up? We're going to look at that on the next slide. So here's that question again. What change must you make if you want the output PD to increase as the temperature increases? So the answer here is to effectively swap round the two resistors. So if we move this across, now we've got our thermistor here and our normal resistor here. Why is that going to make a difference? Well, let's go through it again in exactly the same way. So let's start with the same question. What happens to the output as the temperature increases? We're going to get an increase in the temperature, and therefore the resistance of that thermistor is going to go down. And again, thinking about Ohm's law, I'll write it out for you again. I'll keep doing it. V is equal to IR. If the resistance is going down, the voltage is going to go down. And so we're going to get a decrease in the potential difference across the thermistor. Now, here's the important bit. Because of the fact that the two resistors must add up to the resistance of the cell, so if I call this one V1, that one V2, and that one VT, VT must equal to V1 plus V2. And so if, in this case, V1 is decreasing, V2 must be increasing. So we're going to get an increase in the potential difference across the resistor. Then fall back to what we know about parallel circuits. These two are in parallel, and so if the PD across the resistor is going up, the output PD is going up. So by swapping the resistor and the thermistor, we've completely reversed the operation of our circuit. So now as the temperature goes up, the output PD goes up. So I might use this circuit for something like an automatic fan. So as it gets hotter, the fan blows more rigorously, and so it cools me down more. Okay, and got another one here. Rather than having a thermistor here, I've got an LDR, a light-dependent resistor. The question I'm being asked is what happens to the output as the light intensity decreases. So as the amount of light shines on this LDR goes down, what's going to happen to the output PD? As the light intensity goes down, we know from what we know about LDRs, its resistance is going to go up. And again, coming on to V is equal to IR. If the resistance goes up, the voltage must go up. And so we're going to get an increase in the potential difference across that LDR. And because of the fact that LDR is in parallel with the output, they're always going to have the same PD across them. And so if the PD across the LDR has gone up, the PD across the output has gone up. So this might be used in something like street lighting. If I want the street lights to turn on or get brighter as it gets darker, this is the kind of circuit I would use. So again, what change would you make if you wanted the output to decrease as the light intensity decreased? So here, as the light intensity increases, we're getting an increase in the output. What about if I wanted it the other way round? So here's that question. What change would you make if you wanted the output to decrease as the light intensity decreases? It's exactly the same. We're just going to swap these two components around. So I've moved the LDR up to here now, and now the resistor down to here. So again, let's start from scratch, go through it, and hopefully we have to understand why it's made that difference. So what happens to the output as the light intensity decreases? So we'll start with the light intensity going down. If the light intensity has gone down, the resistance of this LDR is actually going to go up. And because of the fact that the resistance has gone up, thinking about V is equal to IR, I really am going to do it every time. If that resistance goes up, that voltage is going to go up. So we're going to get an increase in the PD across the LDR. And if the PD across the LDR is going up, the PD across this resistor must come down. So remember, they've got to add up to the PD of the cell. And so if one goes up, the other one's got to come down. So the PD across that resistor is going to decrease. And because of the fact that that is in... Oh, no, there we go. Because of the fact that this resistor is in parallel with that output, the PD across them are always the same. And so if the PD across the resistor has gone down, the output PD has gone down. So whereas in the last circuit, as the light intensity went down, the output went up, here, as the light intensity goes down, the output goes down. I'm going to struggle here to think off the top of my head of something that would actually utilize this, but there must be something. Okay, so just to summarize what you should now be able to do, I think after this lesson, you should be able to explain how LDRs and thermistors are used in potential divider circuits, and you should be able to answer questions related to how the output PD or the PD across the components within a potential divider circuit containing LDRs and thermistors vary as changes to the environment occur, i.e. you need to effectively be able to reproduce this step-by-step kind of logical deduction of how we get from a change in the environment, i.e. light intensity, to a change in the output potential difference. Again, like I said yesterday, if any of this doesn't make sense, go back, watch the video again, and if it still doesn't make any sense, send me an email, come along to the drop-in session on Thursday mornings, and you can ask me questions. I can go through it with you one-to-one, and hopefully it will make a little bit more sense.